Yeah. So, good evening, everyone, and welcome to the live session. Um, Sorry, this got a bit delayed today. Uh, I will first wait for your questions if you have. So, please type in your questions. The agenda today is I promised that I will solve the assignment problems, or rather, I will help you solve the assignment problems which are due for submission. I will not give you the answer, but question by question, we can discuss what needs to be done. But before that, if you have any questions, please type it right away. So I'll first wait for your questions. Before we start getting into this assignment. Give me a minute. I'm coming to that. So in this week, we had talked about mode field diameter. We talked about dispersion. And in dispersion, we talked about two types of dispersion, which is in multimode fibers, we talked about intermodal dispersion. And we also derived the bitrate distance product. Then we moved on to single mode fiber, and we talked about the material dispersion and waveguide dispersion. So there are three kinds of dispersion we talked about, and the total dispersion. And there was one more. So this was a week full of dispersions. So there was one more dispersion we talked about, which is the polarization mode dispersion, which is essentially because the two polarizations were walking off at two different speeds. So that was polarization dispersion. Okay. So now let me start answering the questions. Michael Jordan asks, how much polarization extinction ratio is acceptable at receiver side in dual polarization phase modulation system? This is actually an excellent question. So in a dual polarization modulation scenario, what really happens is you send, let's say, two orthogonal polarizations, data into orthogonal polarizations X and Y. That's what you plan to transmit through the fiber. It goes through the fiber. And what really happens is that you were expecting something in this direction, but what you would end up getting is something like this. Right? If I sketch the plane that is orthogonal to the direction of propagation, it will be like something like this. You had, let's say, transmitted along the X direction and the Y direction. What you will end up getting is, if I don't consider the dispersion, what I will end up getting is a rotated version of this, in the sense that the x may have rotated to, let's say, this, and the y may have rotated to, let's say, this. Right? So let me just redraw so that it's all, you transmitted along the x direction, but what you ended up getting is a rotated version of x got rotated this way. And you put in a polarizer along the x direction. So what you will end up getting is only the component of this along the x direction. Right? So, so after transmission, let's say you put in a polarization beam splitter, which will split it into a polarization beam splitter, which will split into the component x direction and, let's say, y direction. What you will end up getting is along the x direction, you had originally transmitted, okay, sorry, this reference is not correct. Let's choose this reference in such a way that, let's say, this is x reference and this is my y reference, right? Now you put a polarization controller at the, or the PBS, or a polarization beam splitter, which is essentially a polarizer which picks the x polarization and y polarization. So you would expect that all this x polarization which you had transmitted here, all the x polarization which you had transmitted here will appear along this. But what happens is, as it propagates through the fiber, the polarization rotates. So which means that what you will end up getting is a rotated version of x polarization. So the component of this x polarization, so the component of x polarization that you transmitted along the x polarization at the receiver, you will have, let's say, a cos theta component here. And similarly, the y polarization would have also rotated, and you will get only a component along the y direction. What is more damaging is that there is a component of y along the x direction, and there is a component of x along the y direction. Right? So you will, if your input is, let's say you call your input as Sx, symbol x and y, or let's say your transmitted symbols are represented as Sx and Sy. What you will end up getting at the receiver, Rx, Ry, is actually a rotational transformation. So that is cos theta minus sin theta minus sin theta, cos theta sin theta minus. Let's not put it as cos theta sin theta. Let's just look at it as, let's say, A11, A12, A21, A22. Later in the course, we are talking about this transformation in detail, and how to actually derotate we are talking about. So what will end up happening is, along the x direction, you actually get a A11 Sx plus A22 Sy, a component of Sx along the x direction, which is the A11 fraction, and not just that, a component of y along the x direction, which is this component, and that's not desired. Similarly, in the Ry, you will end up getting A21 Sx plus A22 Sy. Right? That's also not desired. Now, here you have assumed that there is no dispersion, which means there is no delay between the propagation of along the x and y direction. You are just assuming polarization mixing. Okay. So what you will end up having is, rather than asking the question, what should be the polarization extinction at the receiver, what you should ask is, what is this mixing matrix, and is this mixing matrix unitary matrix, so that I can invert it and get back my Sx, because what I transmitted is Sx and Sy, but what I received is some linear combination of, so what I received is, along Rx I received this, and along Ry I received this. So I should be able to eliminate. So I have two equations and I actually have four unknowns. But because this is a, if you impose certain special properties for this transformation matrix. Rotation matrix has some special properties. Then these A1, A2, A21 and A22, they are not completely independent parameters. You can write them in terms of two variables. So we will talk about it in the later part of the course. But to give you an idea, so the question that you would ask is, how much is this transform matrix? How much is the what is the transformation matrix, and can I invert this transformation matrix? Now, this is the simplest case, an ideal case, and if it happens just as a rotation, there's absolutely no problem. But what really happens in communication polarization multiplex system is also that it's not just the rotation. We just learned that the X component and the Y component will start walking off. If this is the X component, this is the data and Y component, there is a delay. Now, how do I represent the delay in this kind of matrix form? It's just by demanding that there is a phase difference between X and Y component, which means I demand that this transfer matrix becomes, the elements of the transfer matrix becomes complex. There is a phase delay between that. If I account for that, and if I'm able to invert with this phase delay, I can still, if it's a fixed phase delay, I should be able to retrieve. But the problem is that the polarization mixing or the polarization dispersion is a statistical quantity. It is not a fixed phase delay. Unlike chromatic dispersion, which is more or less a constant, this polarization dispersion, the work off between the X and Y polarization is not a constant. It is a statistically changing number, so it becomes somewhat little hard to correct for this impairment. So the best way to do is to avoid it. I mean, you make sure that the delay because of polarization dispersion is much smaller when compared to the bit slot, so that you are not, your bits are not dispersed because of polarization dispersion. Now, since we are talking about these, there's one more. So first thing is rotation. The second thing is polarization mode dispersion, PMD, which is the delay. And the third issue you will find in polarization multiplex systems is polarization dependent loss, which means that there is something in your system which attenuates one polarization more than the other. There could be some component in your system, right? You had communication system has a lot of components on the way. There could be isolators, there could be EDFAs, there could be filters, and so on. By chance, if you will learn about polarization components which introduce polarization dependent loss later in the course. But by chance, just now for now, imagine that if you have a component which is posing different loss to two different polarization, then this picture changes. What happens is this unitary property of this matrix, this nice transformation rotation property, that the rotational matrix, it changes simply because you could do this only when your X component and the Y component had the same length. But then if your X component and the Y component have different lengths, which means that they have different loss, they have different strength, then this becomes non-unitary, and then you are stuck with this problem that you have only two knowns and you have to find four unknowns. That Okay. Please alert me when my second connection is going off because I'm not able to see that. Yeah. Yeah. Okay. So we are back again. I'm sorry, there's some issue with the network in IIT today. So we hope we will be able to continue without interruptions. So, so what I was saying was, whenever you talk about polarization, multiplexed dual polarization transmission, you have to worry about polarization rotation, which can be corrected using the delay, where these elements now will start becoming complex in the sense that to represent the phase difference between the X and the Y polarizations. And the most dangerous is polarization dependent loss. Even delay is not a good idea because this delay is not a fixed delay like chromatic dispersion. It keeps changing. So that's very difficult to handle. So the way typically we try to handle it is to avoid the PMD. The third and the most significant issue is the polarization dependent loss, which means that there is some element in your link which is polarization dependent, which is providing a loss or providing an attenuation which is dependent on the polarization. It is attenuating the X polarization, say for example, more than the Y polarization, right? So that becomes again one more that if you have that, what will happen is this nice properties of this transform matrix will just disappear. Then you're left with two equations and four unknowns, and that becomes a harder problem to solve. So in terms of what is the extinction ratio, you see, you can't talk about extinction ratio here because you get your information in the mixed form, right? The X and Y are mixed, and so what you will get is a combination like this, right? And this combination, so long as it is just a rotational transformation, it is fine. But what you should ask in terms of extinction is when you started transmission in your SX and SY, what was the extinction ratio? So if you generated your SX and let's say you generated your SY, is there a part of SY in SX? That's the extinction that you're talking about, right? The strength of the Y component when you're trying to measure the X component. So long as it's greater than the strength of the Y component is less than 20 dB, which means 100 times lower than the strength of the X component. That means, let me repeat, so long as the strength of the Y component that is appearing in the X direction, X polarization direction, is less than 100 times, it is still fit for polarization multiplex transmission. The channel does not, channel of course mixes the polarization, and later in one of the weeks we will see how to tackle this problem of derotating. But even if the polarization gets mixed, you get a fraction of, you get a large part of X in the Y polarization, large part of Y data in the X polarization, it's still okay, right? A related question is asked by Ranjit, how does delay affect the transmission? Oh, so the delay will greatly affect the transmission simply because of this reason. Again, we will talk about it in detail in the later part of the course, but then I'll just say. So let's say this is the data in the X polarization, and this is the data in the Y polarization, right? This is the bit on. I'm drawing as a function of time, right? I had data which was, let's say, high in the X polarization. I had a data which is again high in the Y polarization. So how did we understand chromatic dispersion? We understood chromatic dispersion by saying that, look, I have a bit which is like this, right? And as a result of the chromatic dispersion, the consequence in the time domain is that the bit started broadening. So it started broadening like this. And when it started broadening, for example, in this particular slot, if there is sufficient energy, I might say this is 1. I might demodulate by mistake that this is 1. And I might demodulate this as 0 if the dispersion kind of completely flattened the pulse, right? That's how I understand chromatic dispersion. Now, how do I understand PMD? So it means that if you have a delay, it means that one of the components is traveling faster and the other component is traveling, let's say, slower. So you had a 1, 0 and a 1 in expolarization. Sorry, 1 should be of the same heights. Let's say 1, 0, 1 traveling along the expolarization. It's a very crude picture I'm drawing. And in the Y polarization, if it is coming after a delay, which means the let's say a 1 has appeared here and a 0 has appeared here and a 1 has appeared here, and this is how the Y polarization is propagating. At the receiver, what I measure is actually a fraction of y in the x direction and a fraction of x in the y direction, right? That's what I just explained. What you get is Rx is A11, a component of x and also a component of y. So in that case, what I will get is, this one, this component appears here and this component appears here. So what you will end up getting is something like this. So you will start misrepresenting, misreading the signals even after you decompose it into the correct polarization, because when you decompose, you are trying to use a transform matrix like this, and if you are not, so what will happen is this A11 Sx and A22 Sy, this is not combining at the same instant of time. The Sx at one instant of time t1 is combining with Sy at some other instant of time t2, right? If this is t1, this is t1, if there was no delay, you are combining them at the same instance of time. But then if there is a delay between them, you are combining them at different instant of time, and so demodulation becomes extremely difficult. Okay, so that's how the delay will affect the transmission. The bit starts spreading because of that also. And what we are saying is that this delay is not a fixed quantity, it's a statistical quantity. Okay, let's go back to the original questions. Can I get the soft copy of the book? So we are getting the notes ready. So by tonight, you should be able to get a significant amount of, or maybe let's promise this week, you will get some significant amount of notes ready. Other than that, I don't have any soft copy of the book. You will have to find out if there are any open source for that. There's a question from Shakti. What are the parameters that affects the channel spacing in communication? So I think you're talking about spacing in the WDM channels. So if your channels are very widely spaced, you know that when you're trying to modulate it at a specific baud rate, let's say B gigabaud, for instance, you know that the first nulls will start appearing in an NRZ modulation. The first nulls will start appearing at the carrier frequency plus B and FC minus B. Right now, how you if the channels are very widely spaced, you can possibly extend this, but how far you can extend is decided by how fast you can modulate. So that's decided by the electronics. And the current state of the art electronics can do up to 56 gigabaud. Right? So you can, the next generation standards are expected to happen at 56 gigabaud, which means that your carrier frequency plus 56 and carrier frequency minus 56 if you're doing non-return to zero modulation. So that actually decides your channel spacing. And of course, you would also want to leave a guard band if you wish to, so that the intersymbol, the nonlinear mixing is prevented, or there's no spectral leakage between the channels. So ITU has come up with some standards, and there are different standards. The one standard is corresponding to 100 gigahertz channel spacing, dense WDM. The dense WDM, you also have a standards corresponding to 50 gigahertz, and there is also a standard which corresponds to 25 gigahertz, right? So obviously, if you make it 25 gigahertz, your baud rate is smaller. So the recent trend is actually to use what is called as elastic grid. which says that you have grid defined by ITU. Last time we talked about the role of ITU in defining the standards and so on. You say you have F1 to, let's say, Fn in the grid. And let's say what ITU does is it basically fixes these F1, F2, etc., which are 25 gigahertz apart. And then you leave it, it's an elastic grid, which means that you leave it to the operator to decide whether he wants to use, let's say from here to here, whether he wants to use these three, he could, or these four, for instance, where he could use, for instance, a carrier at this and occupy this entire band by a large baud rate, or you leave it to the operator to say that, okay, occupy this grid with a very small baud rate. So that is flexible networking is what is proposed in the elastic grid. That is again starting to get adapted in communication systems. The next question is from ANR. Accumulated dispersion and the total dispersion is the same. So whenever we talk about dispersion, we know that we have material dispersion and we have waveguide dispersion, and I'm talking about single mode fibers, right? And the total is your total dispersion, right? The sum of the material dispersion and the waveguide dispersion is your total dispersion. Now, this total dispersion is 17 picosecond per kilometer nanometer at 1550 nanometer for a commercial G652 grade standard single mode fiber. Now, this is a number which is defined as a spread of 17 picosecond for every kilometer of propagation for every nanometer of the spectral width of the source. So when you say total dispersion, this is in this. So this is your total dispersion. But when you say accumulated dispersion, you typically find out what is the dispersion after a length of fiber, right? So let's say I have a source which has a modulation, let's say, of source with the laser. So the line width is of the order of kilohertz. That is not really, or several hundreds of kilohertz. That is not contributing to the delta lambda. What contributes to the delta lambda is the modulation. So this is FC and this is FC plus B, where B is the baud rate. This is FC minus B. So your delta F is actually 2B in case of NRZ modulation, right? There is a tutorial assignment problem also in the same lines. Delta F is 2B in, so for example, if I do 10 giga baud modulation, the delta F, the occupied spectrum is 20 gigahertz, right? And corresponding delta lambda I can calculate. And how do I calculate? I start with C is equal to F lambda. So lambda is F by C, or sorry. So F is equal to C by lambda. So delta F is equal to mod, I mean, we have done this multiple times, C by lambda square delta lambda. So you can substitute lambda as 1550 nanometer. Let's say the center wavelength is 1550 nanometer. Delta F is 20 gigahertz. You can calculate delta lambda. And typically the order of magnitude is, it will turn out that 1 nanometer at 1550 would correspond to 125 gigahertz, right? So you can calculate what is it corresponding to 20 gigahertz. I mean, you can work out this. What I'm trying to say is that you know what is the delta lambda at the source. You know what is the total dispersion, right? So what is the accumulated dispersion? The accumulated dispersion is, let's say this L is in certain kilometers, right? It could be, one span is typically 80 kilometers, so L is, let's say, 80 kilometers. So accumulated dispersion in this case would be delta lambda corresponding to 20 gigahertz multiplied by length in this delta lambda corresponding to 20 gigahertz in the units of nanometer multiplied by L in kilometer multiplied by 17 picosecond per kilometer nanometer. That is the accumulated dispersion. Okay, so 10 gigahertz is 0.08 nanometer. So 20 gigahertz is roughly 0.16 nanometer. You can work it out. Multiplied by length is, let's say if this is 80 kilometer, this is multiplied by 80 kilometer, multiplied by 17 picosecond per kilometer nanometer. This number is my accumulated dispersion. So this tells you how much is the spread that you will have in the time domain. So that's the difference between accumulated dispersion and total dispersion. The next question I have is, Michael Jordan says, will polarization division multiplexing be possible? Yes, it is possible. So all what we were talking about is, I think in the first or second week, I told you the current communication system uses QPSK transmission and also multiplexing in two polarizations. You can do orthogonal polarization multiplexing. What should be the laser's polarization extinction should be? Yeah, so that's what I said at the transmitter. You're looking at the transmitter. Polarization extinction of greater than 20 dB is fine for polarization multiplexed transmission system. Typically, lasers come with polarization extinction of 30 dB or so. That should be the number that you need to target. But more than the laser, what will happen is you are using modulators. So the constraint is by from the polarization extinction of the modulator rather than the laser. Laser typically comes with larger polarization extinctions. Okay, what else is the other question? There was a request from somebody in the forum asking me to explain the mode concept. There was an explanation in lecture 42 where we were using the ray picture to explain the modes. So there was a request to explain that once again because the diagrams were overwritten. So I'm just going to do that quickly. The ray optics picture to justify modes. So in the meantime, if you have any other questions, please go ahead and write it down. What we are saying is that, let's say this is the core of the fiber and you have the cladding here. And obviously you the whole guidance is because of total internal reflection. So let us ignore the change of angle at this interface. What is interesting to us is this interface. If the angle of incidence here is greater than the critical angle, if theta I is greater than theta C, we know that that particular all those rays which are going in with angles of incidence greater than critical angle should get ideally supported in the fiber. So it will appear that you can launch this light at a continuum of angles whose, for example, let's say theta I is, let's say it turns out to be 50 degrees. Now, what is the limit of theta I? It can go from, let's say theta C is 50 degree. The critical angle is 50 degree. It means that any launch angle such that this theta I is greater than 50 degrees. So within the range from 50 degree to 90 degree, if you launch at any angle in that range, in principle should be guided by the fiber. Now what we are trying to say is that, look, that is not possible simply because light does not propagate as rays. We have to also respect the wave picture of light. We should make sure that what is sustained in the fiber, because the dimension of the fiber is really small, of the order of wavelengths. So we should also respect the wave theory, right? And when you start doing that, what you will end up finding out is that not all angles are possible. Only certain discrete angles are possible. And those discrete angles correspond to the modes of the fiber. Now, how do I justify that? So what I demand is that even, so the basic thing that we need to understand there is if the connection between the ray picture and the wave picture. So if you have a ray propagating in this direction and we make a gross approximation saying that we are dealing with plane waves, right? And we know in a waveguide it's not really plane waves, but then to just understanding purpose, we will take it as a plane wave. The wave fronts are orthogonal. Now, what are wavefronts? Wavefronts are the locus of all those, the surface which has points in space which have the same phase, right? That's the wavefront. Now, a plane wavefront means that the wave is propagating in this, the k vector is in this direction, the propagation vector is in that direction. In a plane, this is how the wave is propagating. If I take an orthogonal plane, the phase at every point in space in this plane is going to be constant. That is the plane wavefront. So if I take a ray like this, so this is this red ray. Let me call this as a red ray. Let me call this as AB, ray AB. If this is to be a ray, the corresponding wavefront is orthogonal to this. So I can imagine that these are the wavefronts corresponding to the this particular ray. And you can also imagine corresponding wavefronts to the ray, which is BC. The demand we are making is that if this point, let me extend this wavefront, and let's say that it is hitting this point. So I'm extending this particular wavefront. Why this particular wavefront? Because this wavefront seemed to belong to this point, this ray BC, as well as the ray AB. Now, if they belong to the same wavefront, which means that they have the same phase, it means that, let me call this as, let's call this point as D, this point as D. If D and C should have the same phase, why should D and C have the same phase? D and C should have the same phase simply because they're a part of the same wavefront. Okay, so if for constructive interference at this point, this D and C should have the same phase. It means that the extra phase, because of this propagation from D to B and B to C, this DB plus BC, right? This path difference must be equal to multiple of lambda, or the corresponding phase difference must be an integral, the phase difference corresponding. So dB plus BC is the path. The phase difference corresponding to the path dB plus BC must be equal to m times 2 pi, multiple of lambda. Right? Now you can actually find out what is the now the question is, how do you convert path difference to phase difference? We know that path of lambda corresponds to a phase of 2 pi. So a path difference of dB plus BC will correspond to dB plus BC times 2 pi by lambda. This must be equal to m times 2 pi. Now we added a delta here to account for any phase change because of deflection, right? Then what you did was simple algebra. What we said was, let's say this angle is theta, this angle is also theta. So which means that this angle is theta, this angle is theta, which means this angle DBC is 2 theta. And this angle is 90 degree. This angle is 90 degree simply because, we mark it in red. This is 90 degree simply because it's a plane wavefront, and the wavefront is orthogonal to the direction of the ray. And you do the trigonometry, you can write down dB and BC in terms of this D. That's what we did. We said that we can always write BC. So if this is theta, this is 90 degree, right? Here again is theta. So I can say that cos theta is equal to adjacent side, which is D divided by BC. So D is equal to, sorry, BC is equal to, because we want to find BC, is equal to D sec theta. So I got BC as D sec theta. Now what about DB? It is this one. Now if you take this triangle which I'm shading here now, right? In that triangle, if you choose to find out what is cos 2 theta, because this angle is half is theta and the remaining half is theta. So the total angle is 2 theta. Cos 2 theta is BD divided by BC, because BC is again the hypotenuse. So which means BD or DB is equal to BC cos 2 theta. So you substitute this and this here, and you will end up with the condition for the allowed values of theta. And that part is explained in the lectures. So I hope that is answered. I have a question from Abhimanyu. If I want to design optical fiber laser system, how can I calculate the cost and time required for that? So that's a very common on the content in week 6. Maybe we'll take this up towards the end of the course, where you now know, you will be able to answer this question yourself. Because by the end of the course, if you were following the course very patiently, you will know how to build the optical fiber communication system, and it is not very complicated. The next question is, what is beta 2? So beta 2 is another way of explaining dispersion. So the dispersion is quantified. This is explained in the videos properly. Please go through the videos, but I don't mind repeating it. Dispersion is again, I lost the video. I hope you can. See my video now. Yeah, so this was a question related to beta 2. So dispersion is quantified in two different ways. One is through dispersion parameter. Dispersion D, and you have the dispersion coefficient beta 2. Okay. Now I have an explanation in class. I had discussed what is the difference between D and beta 2, but I can do this once again. The way to go about defining this is the following. Let's say I have a pulse. I would actually refer to the video. I've done a better job in those videos. I think it is appearing in, I can tell you the exact video where I have in phase velocity, group velocity 1 and phase velocity, group velocity 2. Please go through that content once again. And for now, I will just say that both of them quantify dispersion. D is in picosecond per kilometer nanometer, and beta 2 is in picosecond square per kilometer. And D is actually related to beta 2. I mean, you can, that's derived in class. So D is equal to beta 2 times minus 2 pi c divided by lambda square. This is also derived in class. So please go through that once again. The question by Michael, dispersion equation, do we need to consider light speed same as in vacuum or C divided by fiber refractive index? I got assignment's answer coincide with the vacuum speed of light. Right. So again, now we are getting into the assignment. So let's just look at the assignment questions. Let's go to the first question. You have just to quickly answer Michael's question, lambda naught. Whenever we say we have tried to use the notation lambda naught, that actually talks about lambda in free space. So when you say dn by d lambda naught, d square n by d lambda naught square, so that would actually represent in free space. The fact that it is in the material is already considered in when you're properly see, you cannot directly divide it by the core refractive index because after all the propagates as modes in the fiber. So if you were to really calculate what is the speed in the medium, you should actually divide the lambda with you should actually divide the lambda with the effective index of the mode, right? So in that sense, all what we will use is in free space. I hope that clarifies. So the question 1 is about calculating. So you were given. I hope you can still see my screen. Yeah. So in the assignment questions number 6, a table of V. So the question 1 is where the data is given for V, d by dV of BV and d square by dV square of yeah. Sorry, there's an issue with the connection again. My laptop. Has this tablet is not getting connected. Give me a minute. So let's just discuss it while we're waiting for this connection. So you have the data for V, first differential of BV, and the second differential V times second differential of BV. The first part. The first part is to calculate the material dispersion. Second part is waveguide dispersion. Third part is total dispersion. Okay. So now material dispersion, you know how to calculate material dispersion. We derived in class that it is minus lambda by C d square n by d lambda square. Right. So that is information is given. You have lambda is given as 1540. Dn by d lambda is given. D square n by d lambda square is also given. So use the value in free space because that's how we derived. We started with free space only. Right. So So it's a mere question of substituting these parameters. You will get your answer. The second question was waveguide dispersion. Now for waveguide dispersion, again, we derived the expression for waveguide dispersion in terms of BV. So what is the philosophy of having waveguide dispersion? Even though you don't have material dispersion, even though N1 and N2 are independent of lambda, you know that the normalized propagation constant, which is your B, that becomes a function of lambda because your B is beta square by k naught square minus N2 square by N1 square minus N2 square, right? So you say that B is a function of lambda. So you did a first derivative of B with respect to lambda and in fact with respect to omega, and then you calculated what is the dispersion there, and that number turned out to be something like minus N2 by C. We derived in class minus N2 by C delta 1 by lambda V d square BV. So it's again a formula substitution. It's just that we have to, when we started deriving this, all this were done for free space, so you should use free space wavelengths only. Beta 2, again, we derived the conversion from, so we got the material dispersion and the waveguide dispersion, so you can calculate the total dispersion. Now, once you have the total dispersion, you can calculate beta 2 because we just discussed how beta 2 gets related to D. So that's the next one. Accumulated dispersion, again, accumulated dispersion is operating at some 1540. Since delta lambda is not given to you, right? So I will not be able to multiply the delta lambda because that information is not given. So that's why it says accumulated dispersion per nanometer. So all what we need to do is to calculate the, multiply the dispersion parameter multiplied by the length of the fiber. That's all what you need to do. The next question is about accumulated dispersion for a 10 Gbps system. So this is what I was pointing out. Now you have enough information to calculate what is the delta lambda for a 10 Gbps system. Now I gave at 1550 nanometer numbers. You have to now solve it for 1540 nanometer. You have to calculate what is the delta lambda corresponding to 20 gigahertz because 10 Gbps will have its first null on 10 gigahertz on either side of the carrier. So the delta frequency, delta F is 20 gigahertz. Corresponding to that, you calculate what is the delta lambda, and that you will use to find out the accumulated dispersion. The next one is what is the dispersion parameter to compensate for accumulated dispersion? Suppose you were to compensate, you were to cancel off the dispersion. Then you need to find out what is the dispersion. So let's say you want to now compensate this accumulated dispersion with another fiber with a shorter length. What should be the dispersion of that fiber if that length of the second fiber is 10 kilometers? So let's say the accumulated dispersion after 100 kilometers turned out to be minus 500. Let's say I'm just giving an example, minus 500 picosecond. Right now, minus 500 picosecond per in that question. So if you were to cancel out, what you should do is to use another fiber whose dispersion is positive. Instead of minus 500, the accumulated dispersion should be plus 500. Now, plus 500, you want to get in 10 kilometers length. So what should it be per kilometer? So you can say plus 500 divided by 10 kilometers. So that's 50 picosecond per kilometer nanometer. Everything you can calculate in per nanometer basis. So that's how you would calculate what is the accumulated dispersion that is required to compensate for that. Again, the same thing for 10 Gbps NRZ system. So the answer will not be in per nanometer. It will be, you can now calculate in the parameter, dispersion parameter is going to be the same, because that's not, dispersion parameter is always picosecond per kilometer nanometer. So you will, that answer is not going to change whether it is 10 Gbps system or 20 Gbps system, because it's a per nanometer quantity, right? The accumulated dispersion will change, but the dispersion parameter is not going to change. Okay. Now, question 7 was the case of a dense WDM system. So we talked about it last time, that there's a 1530 to 1560 band. So the key here is that the delta lambda to delta F conversion is a lambda dependent quantity, which means that the spacing between the channels, I told you this last time also, the grid spacing is in terms of frequency, because that's a unique quantity, is not dependent on lambda. Whereas as you move from 1530 to 1560 nanometer, this conversion delta nu is equal to C by lambda square delta lambda. For the same delta nu, as lambda increases, to keep the delta nu the same, your delta lambda has to also increase. Only then the delta nu will remain the same, right? So it's because of that inverse relation between nu and lambda. So you can calculate what is the delta lambda corresponding to 100 gigahertz at 1530 nanometer. You can calculate it at 1560 nanometer as a center frequency. The delta lambda you will get is different, right? So that's the idea of this question. Given D is equal to something, the phase mismatch for generation of high frequency. So the phase mismatch is actually delta beta, which is beta 2 times the frequency separation, right? So that if the frequency separation is 50 gigahertz, so where is this phase mismatch or phase difference coming from? You see the colors propagate with different speeds, and so the accumulated phase is different, and that difference in accumulated phase is what you're calling as phase mismatch, right? So in terms of group velocity dispersion, you can calculate that phase mismatch beta 2 as that delta beta as beta 2 times the frequency separation square, right? If the frequency separation is 50 gigahertz, you can calculate what is the corresponding radiant frequency separation, multiply it with beta 2, you get your answer. The next question is number of capacity of the WDM system covering this entire region using 40. So if you have acceptable loss over 1.3 to 1.6 micron, which means that you are able to fill all the grid spacing from 1300 to 1600 nanometer, you're trying to find out what is the total capacity. So you have to calculate how many frequencies can be used. So from 1300 to 1600 nanometer, you can find out how many 50 gigahertz spaced lines can be put in, and that multiplied by 40 gigabits per second will give you the total capacity. Okay, so all what you need to do is convert 1300 nanometer to frequency, convert 1600 nanometer to frequency. So you are calculating the absolute frequency corresponding to 1300 and 1600. The separation between them will be the available band. In that available band, you are now placing 50 gigahertz grid. You find out how many 50 gigahertz lines can you place in that available band, and each grid is able to carry 40 Gbps. So you calculate what is the total capacity. Then the same question of similar question for C and L band. So that is again calculating the number of channels. The grid spacing is different, 1530 to 1610 nanometer, and the bitrate distance product. So we have derived how to calculate the bitrate distance product. So you can use these numbers to calculate what is the bitrate distance product. So that's about this assignments. Now I want to see if you have any other questions.
If there are no more questions, we will wind up. I would request you to please post it in the forum if you have any further questions. Thank you. We will meet again on next Thursday and we will discuss the content in week 7.